So good afternoon, everyone. Welcome to the first ever KubeCon India. I hope everyone is excited about the sessions that have already occurred and are excited of what's about to come next. I'm Kush Trivedi, Senior Platform Engineer at EarnIn's.
Hello, everyone. Thank you. Good afternoon. Really excited to be here as well. This is Somnath Chakraborty, Platform Engineering Manager in EarnIn's in Bangalore, India.
So before we get started, by the number of raised hands, can I know how many of us here are using a service mesh? Cool. And how many of us here are looking to adopt a service mesh in near future? Decent. So in this talk, we are going to cover EarnIn's network evaluation with Linkerd. We are going to cover a very brief introduction about what are we, what are our challenges, what the problems with our older service mesh were. We went into the market, we analyzed all the available service mesh, how we decided which service mesh to adopt, how our migration journey looked like, and how our success looked like. So without wasting any further seconds, I'll hand it over to my colleague Somnath.
Thank you, Kush. So to start with, let me begin on what is EarnIn's, who we are. EarnIn's, founded in 2013, is a fintech company on a mission to provide financial wellness and continuous cash flow for individuals. We are a first-of-its-kind platform that gives our customer on-demand early wage access, which enables them to access their earned money as is when they earn it. Since our launch, over 4 million customers have accessed more than $20 billion in earnings through our app. So let's talk about EarnIn's ecosystem and why we adopted a service mesh. At EarnIn's, we manage over 500 microservices distributed across multiple EKS clusters, running more than 10,000 pods. This scale is essential to support the massive traffic that we handle, which is over 4 billion requests every month. Given this complexity, we recognize the need for better visibility and control over how our services communicate. Relying on traditional monitoring methods like application monitoring often felt like flying blind. Since we did not have granular details on our network, we needed a better approach to understand how it is behaving to ensure more reliability and efficiency. On top of that, we also needed a reliable service discovery as well, and some add-on features like retry and timeouts, which could be implemented on our network. However, as we keep on progressing in our journey, we started discovering significant bottlenecks in our existing enterprise service mesh. Instead of being a boon, these issues were creating operational inefficiencies and impacting the benefits we aim to achieve in this journey. So now let's get into a little more detail on what all challenges we had in our existing service mesh. First of all, the solution was extremely resource heavy. It was consuming excessive resources for most of our services. This created inefficiencies and led to higher operational costs without adding proportional value. Operations like lifecycle management of the mesh, including maintenance, upgrades, and downgrades, were also quite complex without a proper definitive guide. This gave rise to higher operational overhead for our engineers. Another critical issue was the lack of community support. Without a strong open source community backing it, we had to rely solely on the enterprise support to resolve our issues, which often delayed troubleshooting and slowed down our enhancements. We also struggled with observability. There were limited insights into the key network operations like inter-cluster traffic flow and service-to-service communication. We lacked visualizations and deeper insights into the control and data plane matrices, thus making it challenging for us to know how these components were behaving. Lastly, the absence of control plane administration was a major gap. We did not have control plane management, and we were not exposed to all the available configurations of the control plane, which was a big hurdle for us in ramping up of our adoption. These challenges mandated that we need a better service mesh which will support our scale and operational needs. So, the journey for searching of a new service mesh began. At the core, we are looking for a very lightweight data plane. We needed minimal resource overhead while ensuring critical features like MTLS for secure communication, retries for resilience, and timeouts for fault tolerance were present. We also wanted complete operational control over the control plane and definitive guides over day-to-day operations and lifecycle management of the mesh. In terms of performance, we wanted significantly lower latency in the sidecar processing time, since each and every request were already intercepted by it. Security was also one of the top priority. We wanted the mesh to give us enough granular control on managing our traffic and help us implementing a zero trust network approach. Additionally, we wanted deeper insights on the network traffic flow, intra-service interactions, and matrices on how the control plane and the data plane are behaving at the service level. We also needed these performance matrices readily available to us for us to consume. Well, a mesh that satisfied all these needs were not just a tool. You can say it was a foundation for a scalable, secure, and an efficient service communication. After analyzing all these requirements, we narrowed our focus down to two leading service mesh solutions, Istio and Linkerd. Both offered a strong feature set which met most of our needs. Let's go through further details in the following slides on how the decision was made between them. Kush, over to you.
Thanks, Somnath. So now let's look at what were the key characteristics which affected our decision to move towards Linkerd instead of Istio. Now, just a side note, this is not a thorough comparison guide between Linkerd feature set and Istio's feature set. This is very specific to what requirements we had at EarnIn in adopting a new service mesh and what were the feature set which we wanted for a specific use cases. The first thing, as Somnath had highlighted in the earlier slides, we wanted a service mesh which is pretty light, can provide us with efficient service discovery, can give us add-on features like MTLS, retries, and timeouts. Given Istio's data plane, which is Envoy proxy, supports a lot of advanced features like native HTTP filters, including gRPC JSON transcoding, GraphQL support. On top of that, custom filters like Lua as well as WASM-based. We didn't think that we require a lot of these advanced features in our journey, which is why to adopt a lighter data plane, and as many of you might already know that Linkerd's data plane is written in Rust, which is quite a performant language and efficient garbage collection language. We went ahead with Linkerd's data plane in this point. Second point, which was a major decision maker, was Istio's ambient model. We were surprised by the sidecarless approach which Istio's community had adopted using ztunnel with a node-based proxy. But during the evaluation time, that feature was still in a beta phase, and we didn't see a lot of enterprises or customers' journey migrating from sidecar to ambient model. As of now, with Istio Release 1.21, this has been promoted to GA, but at that time we were a bit hesitant given our number of microservices as well as the scale of traffic to adopt a beta feature. Last but not the least, few of our team members had some horrific and terrible experiences in managing Envoy proxy as a standalone application or a reverse proxy in the past. They had been using tools like Chef and Ansible to control lifecycle management as well as configuration management, which resulted in Envoy becoming a pain for them. When we were evaluating the sidecar comparison, Envoy proxy made them a little hesitant, which gave a brownie points to Linkerd's data plane. Although it's worth mentioning that over here, Istio takes care of all the heavy lifting in relevance to Envoy. You don't need to take care of any of the individual Envoy configuration, but the control plane of Istio is mature enough to take care of all the data planes. But yet, this was a hesitant decision which we made. We went ahead with Linkerd, and immediately we started the adoption as well as making changes into our network layer. Before we jump into what changes we did in our network layer, as well as how did we do the migration, there are a few salient features which I would like to highlight. Linkerd is a very light mesh, as well as it is very simple to operate. To be honest, if anyone wants to try it out, within few minutes, you can actually install as well as configure Linkerd into a sandbox cluster. You don't need to read a lot of documentation, as well as the learning curve of Linkerd, I would say, is the lowest in all the service mesh which are available out there. Second thing which we wanted to highlight is, as you all know, we were flying blind in terms of service-to-service monitoring, network observability. Linkerd provided us with granular observability matrix as well as dashboard for every service sidecar, as well as the control plane of the complete mesh. We were able to tie in all those metrics with our Prometheus integration and our dashboarding capabilities to have more granular insights on how a network is behaving. Last but not the least, Linkerd does not provide you with an opinionated ingress, but you are free to choose whatever ingress option you want to adopt, whether it's open source or whatever you want to prefer. So now, one of the major changes which we did in our network layer while adopting Linkerd is the ingress change. Our older service mesh had provided us with an opinionated ingress, which we wanted to migrate away since we were using Linkerd. We went out in the market and we analyzed all the available ingresses, majorly which were based on Nginx, which were based on top of Envoy proxy, which were based on top of HA proxy. After a thorough comparison, we were able to decide, or we were left with the options which were Kubernetes NIC controller, as well as F5 Nginx ingress controller. We went ahead with F5 NIC. I wouldn't go into a lot of details, but the most salient feature of F5 NIC, which looked very beneficial for us, was the master minion model. We at EarnIn empower every developer to self-serve their own infrastructure, manage, and create it. With the master minion model, we were able to abstract away all the integrate configurations, all the messy configurations like certificate ARN, domain management, security group IDs, and everything into the master template. As a developer, you would go into our IDP, provide the service name, provide the endpoint details, and within few minutes, we would just create a minion ingress template referring to that master to onboard or create a new ingress for you. So now let's look at how did we start our ingress migration. So we went back and we created two endpoints. Previous slides, please. So we created one different endpoint, which was pointing to the Nginx ingress. We had one older endpoint, which was pointing to our older ingress. We leveraged weighted DNS routing, which gradually shifted traffic from 5% over to 100% from older ingress endpoint to the newer ingress endpoint. We did this complete shift within 1 week so that we make sure that we are not expecting any unexpected challenges or there are no hiccups. Now let's look at what or how we did the mesh migration, or how we migrated our workloads from the older service mesh to Linkerd. One of the early decisions which EarnIn has made during the adoption of Kubernetes was using a centralized Helm chart. We had a single Helm chart which could control each and every type of deployments we had. Although this is very opinionated, but we as an enterprise realized that if we want to enable developers to self-serve them, empower them, we just need a single value configuration interface with which they can create anything they want, whether it's a cron job, whether it's a batch job, whether it's a gRPC service, HTTP service, or whatever they want, instead of creating 6 or 7 different Helm charts for each and every specific service. Now what we did was we enabled dual mesh support in our Helm chart by making sure we can support Linkerd as well as our older mesh at the same time. We raised the PRs in the service repositories to make sure that we are disabling the older mesh configuration and enabling the configuration which annotates the workload namespaces. At the last, we are using GitOps-based continuous deployment workflows to deploy things at EarnIn. So the last step was pretty much automated. As soon as you merge the PR, a rolling restart would be triggered. And with the rolling restart, your new services will have Linkerd sidecar injected instead of the older mesh sidecar. Now let's look at what improvements that Linkerd make to our network layer, as well as what are the features of Linkerd we have adopted till now. One of the key features which we wanted, and as Somnath had highlighted in the earlier slides, that we wanted a better security. As soon as we started adopting Linkerd, the first thing which we enabled was MTLS communication for each and every internal service-to-service communication. We onboarded cron jobs as well as batch jobs into Linkerd. On top of that, after enabling MTLS, we added authorization policies to make sure that only specific clients are able to call a specific service. This authorization policy is not only helped in improving the auditing, but is also helped in tracking what all service-to-client interaction we might have in our cluster. One of the side feature which we achieved using the authorization policies is that suppose you have a Kubernetes cluster which has service A, B, and C deployed. Now one day, a team writes a service D, and that service D starts calling your service B with 1,000 requests per second. The owner team of service B does not know that we are going to get a service D, so they didn't have enough time to capacity plan it. They didn't have enough time to change the HPA configurations. So what would happen is you will see an internal DDoS, your service going down due to another service which was created by you. With this, we were able to abstract away authorization policy management into our internal developer platform. Now, if a new service is coming up, they will need to request an authorization policy change in the server, and the service owner will be able to see, okay, there's a new service which is supposed to call my service. So they would have enough time to capacity plan it without any of those unexpected surprises they might get in prod or any lower environments. Second improvement which we got with Linkerd was the service-to-service communication or transitioning to intra-cluster URLs. As we had highlighted that our older mesh had very intricate configurations and we were not exposed to control plane management, we never really knew that how load balancing for service-to-service calls is working. So for all of our critical paths or our critical services, we were using ALB ingress endpoints for internal service-to-service communication. Now what that means is, for every internal service call, your call will go outside the cluster, come back via ALB, and then it will come back inside the cluster. This was slow because there was an additional hop through the ALB ingress, as well as it was not efficient enough. With transitioning to Linkerd, we were able to get enough confidence in the capabilities. We removed all those ALBs, as well as we transitioned each and every service inside a cluster to use the intra-cluster URLs of all the services. This also reduced the latencies, as well as saved us some few bucks because those ALBs were not in function anymore. Last but not the least, we abstracted away logics like retries, timeouts, circuit breaking from application layer logic to network layer. At EarnIn, we have more than 5 programming languages in which programmers write and deploy their services, not limited to Golang, Python, Kotlin, .NET, and Java. Now to support all of these services, we wanted a language agnostic framework as well as platform compatible framework, which could give us a centralized, reliable way to support all of these features. We integrated all these configuration into our IDP yet again, which reduced the operational complexities for developers on thinking, how do I manage the timeouts, how do I manage the rate limiting, how do I manage the circuit breaking on my service. Rather, Linkerd started doing everything for you. So if you see in the slide over here, this is a very brief overview of how our service-to-service calls or network architecture looks like. After a user calls in our service, it passes through a CDN. Then we have a NLB, which makes sure that the traffic is going to the Nginx ingress. We have already onboarded the Nginx ingress into the Linkerd authorization policies too. So if you want to call any of the service through an external or internal endpoint, you will need to make sure that you are also adding that specific Nginx ingress endpoint to your authorization policies. And for each and every service-to-service call, the call will first get intercepted by the Linkerd sidecar. As we might already know, we will see if the authorization policy rules are evaluated. If it's allowed, the call will be passed. If it's not allowed, the request will fail with 403 by Linkerd itself. There will be no DDoS for your service. Now, let's look at what are the next steps or what are the next set of features which we are looking forward to adopt from Linkerd or the Linkerd community. First and foremost is, as most of you would know, that Linkerd supports native integration with Kubernetes Gateway API project. What it means for us is, we are starting to begin migration from service profiles CRD to HTTP route and gRPC route for enhanced flexibility and standardized traffic management. We are also in progress to roll out progressive deliveries, keeping Linkerd at its core for providing us features like traffic splitting and traffic mirroring for supporting canary deployments and blueprint deployments at EarnIn. We're also looking forward to adopt more and more features of Linkerd. Like as I said in previous slide, we have onboarded all the cron jobs into Linkerd 2, which highlights that how do you make sure that Linkerd await sidecar containers are being inserted. So now we are also in progress to migrate away from the sidecars to Kubernetes native sidecars, which is a recent support Kubernetes community has added in the newer versions. And for those who might not know, there was a newer release of Linkerd 1.17 where there are a lot more features supported by Linkerd which had been requested by the community a few years back, like client-side circuit breaking, server-side rate limiting, federated services for better multi-cluster model management, and a lot more. So yeah, we are looking forward to adopt all of that. And that was our time, folks. We are looking forward to answer any questions anyone would have.
Can you elaborate a bit more on your comparison between classic Istio and Linkerd in terms of sidecar resource usage? Whether it was a point that you considered. Thank you.
So we did install Istio in our sandbox cluster, as well as what we wanted to compare was the canary rollouts, which we are going to support in the future. We used Istio virtual services, as well as we used, I think, Linkerd's or Gateway API's HTTP route. What we saw was, when we are using virtual services for making sure the canary rollout is happening, we were seeing an increased memory usage by the Istio control plane. This is, I think, an issue which is already raised in the Istio Slack community too. Maybe this is something on how Argo rollouts handle the things with virtual service resource, but we have not got a closure yet on that.
And was that not happening with Linkerd?
No. Linkerd's control plane memory usage was pretty much constant. So we have around, as of now, we have around 50 services onboarded to use Argo rollouts as well as Gateway API, HTTP route, and gRPC route. Because Linkerd by native does not support traffic splitting. Earlier, Linkerd used to use SMI, Service Mesh Interface, which is now a deprecated project. So they have moved to Gateway API integration using HTTP route and gRPC route.
Okay. And the other question was whether there was any requirement in the sense support for Linkerd on EKS.
Support on, so as I said, it was a very simple
Okay.
mesh, and we had a lot of operational simplicity.
Right. The reason why I'm asking this is in case of Istio ambient mesh, for example, I think it's due to the nature of ambient mesh itself that you need support from the underlying platform service like EKS or AKS.
For now, recently, what we have done is we have signed up a support contract with Buoyant for now. So
Okay.
I would say for some time we are going to stick with Linkerd.
Okay.
Even one of the key features which we wanted was egress monitoring too, which was not available in Linkerd. But with the newer release, they are also supporting egress monitoring now.
Oh, okay. Great. Thank you.
Monitoring was really one of the major reasons.
So do you see any real-time challenges while upgrading Linkerd versions, like say 2.16 to 2.17?
As of now, nothing yet. We do have a lot of lower environments. We have environments like sandbox, dev, stage, pre-prod, and then production. Whenever a new upgrade occurs, we have, like as I said, we are GitOps based, and we have GitOps based CD capabilities. We are using Argo CD as well as Flux CD for combination of few things. We first try to perform each and every upgrade in the sandbox. If there is any issue, if there is any backward changes, we make sure that we are addressing them in the sandbox first. So up until now, we have not got any of the backward incompatible changes. Like even the changes of moving from service profiles to HTTP route. We made sure that we are trying it in the sandbox environment first before we start going to the higher environments. So maybe this is because of how we have structured our engineering practices and platform. We are not facing any of those.
Thanks.
Yeah, this question is from my previous team, for implementing a service mesh of this kind. The challenge that we met up was to determine the add-in potency of a resource and the retry budgets. So have you implemented any of those?
So coming on the retry budgets, as I highlighted in my slide, those are specific to teams. So a team has capability to modify. Am I audible? Yeah. Coming to the retry budgets, it is specific to per team. We have exposed all those functionalities via IDP around how they can configure what retry policy they want. We do provide the same default policies, but a lot of teams are configured their own retry strategies.
Okay. And about the idempotency of a process?
Idempotency, can you elaborate more on that?
I mean, if your process is duplicated and you would not be able to, differentiate which one is original and which one was duplicated.
I think this is something which your containers might take care of or your service code is take care of. What I think the service mesh, what it does is, it just provides you a way to intercept the traffic and then inject whatever features you want and a
No,
better
but
service
what
discovery.
I had read about this particular service mesh was it is one of the bestest feature to, identify the idempotent process and then kill it.
Maybe we might check into it, but
Okay.
maybe
That's fine.
it's something which I'm not able to get
No.
in terms of idempotent process.
No problem. Yeah, thanks.
Thank you.
I think we heard a lot of the advantages of Linkerd. Do you have any pitfalls or things people should be looking out for when they adopt Linkerd?
I would say one thing, as I had specifically highlighted, that whatever features Linkerd can support, Istio can support too. And one of the things which I mentioned in my slide is Envoy is a feature-rich and advanced sidecar. So let's say if you have a requirement of doing gRPC to HTTP transcoding, which is a lot of organization does have it. A lot of organization try to use everything gRPC inside their systems, but they want to expose HTTP APIs or REST APIs for those services. With Envoy, you can natively use the HTTP and gRPC transcoding filter, which Envoy natively supports. There are more things like using OAuth 2 support with Envoy, using JWT interception with Envoy, where you can implement something like STS or something like internal service-to-service communication authenticator natively on your sidecar. But as I had specifically mentioned, at EarnIn, we had a limited set of requirements. And given our past experiences where we used the bloated service mesh, which resulted in resource overhead, we wanted to be away from using all of those stuff and just keep our focus on what we need and what it can support.
It's not completely about the service mesh, but while you were talking, I just want to know about your internal developer portal. Like, was it something that you created for your own organization or something you're adopting from third parties? Yeah.
We have a third-party vendor.
Okay.
So I'm not sure if it's good for me to name it, but we have a third-party vendor who provides a bare metal or a bootstrap developer portal. What it also provides us is we can write our custom plugins on top of that. So all of these features which I told about, we have written around 8 to 10 custom plugins. We have also written plugins like managing your own AWS secrets in a developer portal, managing your own deployment configurations via a developer portal, and all those stuff. So we have a vendor which provides us a skeleton and a bootstrap where all of your services are there. On top of that, we have the ability to create all the plugins which we want.
Okay, so it's not an open source solution. Like the vendor that you're talking about is.
I don't know the internals, but yeah.
Okay, fine.
And it has been a constant journey on the IDP portals. We have been constantly improving on it. We have been constantly building on top of it. We have, we are, like we can mention, our deployment. Our deployment is also kind of integrated with it. So we are going to integrate with it, if to be precise. So yeah, it is a constant journey. It is a constant evolution, and the ability to keep on adding plugins or develop for it really helps.
One thing on the gateway API, we were comparing Istio and Linkerd, and we found that the gateway compliance for Istio was much better than the Linkerd. And second step is ingress control going to be totally, we have to move it away from as a future development? So these are two different questions which I wanted to understand. Like, what's your perspective on them?
On the gateway API, I think if I say about Envoy or the virtual service CRDs, Istio already has a lot of support or already has most of the support what gateway API aims to offer you. With maybe I'm not officially associated with the Linkerd community by any chance, but Linkerd used to use SMI to provide traffic splitting and mirroring capabilities. And in recent years, SMI was deprecated project. With introduction of Gateway API to replace SMI, and even SMI, which is Service Mesh Interface, has been merged into Gateway API. So there's a strategic transition which Linkerd has done.
That's
to adopt
still
it.
happening, I think.
Yeah.
The Service Mesh
Yes.
API is still under progress. But you see that this gap in compliance to gateway APIs, will this get reduced or will this be maintained? Because clearly when we go through the compliance of gateway, Istio is a clear winner.
So we are
No, that's
to-
the documentation part and
So to be more precise, we are not using Gateway API controller, but we are using Gateway API CRDs. Linkerd has the native support to support those CRDs. So we are just using the Gateway API
so
CRD.
not the Gamma initiative you're saying.
Yeah.
Have you used service profiles with your internal services on Linkerd?
Yes. We are already using service profiles.
Yeah. Sorry.
No, go on.
So have you faced any issues with service level metrics on Linkerd? Because something we are facing right now for the past 2 versions.
When you say service level matrix, would you mind highlighting on what specific?
Things like API level requests, or how much RPS any specific API endpoint is receiving. Have you set up something like that?
So how much RPS and specific API is receiving? I think for that we have APM. Ideally, what we check from the sidecar level matrix is what are the error rate for specific endpoints, how is the traffic flow happening, and if there is any miscellaneous traffic flow happening, or if there is any not allowed traffic flow which is coming in, or if there is any service which is not onward to the mesh trying to call our services.
Okay, so
But
not exactly API level metrics that
Yeah.
I'm talking about. Okay, thanks.
Just following up on his question, do you have a number like the peak throughput that your sidecar, one of your top performance sidecar has served, and how much latency it actually adds, V90 or V90?
On the latency part, this is something which we will be doing. So to support or to get the numbers of the sidecar metric, we will need to annotate or we'll need to use an instrumentation library for Linkerd itself. Where, for now we don't have. So for now what we have done the comparison is, we have our APM provider. What we see is in our APM, let's say one call is giving us 2 milliseconds as the latency. In real world, from our CDN, we see something like 2.2 or 2.15. Again, I'm not sure because there are a lot of network hops given NLB and other things. So we'll need to see how much Linkerd sidecar specifically consuming. I think let's go for lunch now. Thank you everyone.
Thank you all. Thanks for attending.